In this video, we're going to talk about another small signal amplifier. Here, you can see clearly the input V signal is given to the base, connected to the base, and the output is connected to the emitter. Okay, so we have something at the emitter, something at the base. So what will be the common terminal? Collector. So this is called CC configuration, common collector configuration. Now for any configuration, we have to do the DC analysis. So while doing DC analysis, replace all AC sources with their internal resistance. At the same time, if we have a capacitor, capacitor is going to act like open circuit in DC. So here I have a capacitor there with base, connected to base, another capacitor connected to emitter. So replaced them with open circuit. Now we're going to do the DC analysis. By the way, here at emitter, he already gave us the 1 milliampere current source. So definitely there is 1 milliampere current is passing through the emitter. So he already gave us the IE value, emitter, and the beta value is 200 alpha. Based on from the beta value, we can find the alpha equal to beta over beta plus 1. So alpha equal to 0.995, and from that I can find IC because alpha equal to IC over IE. So IC equal to 0.995 milliampere. We need IC to do the AC analysis, so that's the reason I'm finding IC. Once we have IC, now make sure that this transistor working in active mode of operation. So to do that, I found VC first. VC is the voltage at the collector, and we need to find VE. So the VCE, as long as voltage between these two terminals, VCE greater than 0.3 volts, then that transistor is in active mode of operation. So I found VC equal to 10 minus VC equal to 6K times IC. IC is the current passing through this. So I found VC equal to 4.03 volts, and from here I found VB because to find VE, I know if it is in active mode of operation, the voltage drop across this junction is 0.7 volt. So here it is VB, and I know IB current. So based on IB, I found first I found IB, IC over beta. Beta value is 200 given, so that's 4.97 microamperes, and then I found VB equal to 100K times 4.97 micro. It's negative 0.497 volt. That is negative because current is entering from ground. The ground voltage is 0, so this must be a negative value because current always flows from higher potential to lower potential. So here higher potential is 0, so VB must be negative number. So VE is VB minus VE must be 0.7 volt. So based on that, I found VE equal to negative 1.2 volt. So VCE in this case, VC minus VE, which is 4.03 minus of minus 1.2. So definitely it is greater than 0.3 volts. So this transistor is in active mode of operation. Once we know the active mode of operation, we need to find GM, trans conductance, which is IC over VT. These are all common formulas. Doesn't matter whether it is a CB configuration, CC configuration, or CE configuration. R naught is VA over is IC, and RE alpha over GM. Now here is the AC equivalent circuit. Now we are using T model because the emitter is not directly connected to the ground while doing the AC analysis. So we have to use the T model. Remember, the CB configuration and CC configuration, we are not going to have any pi models. Only CE configuration will have both T model as well as pi model. Now I'm going to do the AC analysis. So in AC analysis, our first step is we need to find AV gain, which is V naught over V input. Here input voltage is between these two terminals. So here is my V input and output is across the emitter and ground. Okay, so I need to come up with a relation between output and input. So can I say my V output, so V input is across here and same as here, since those two are in parallel. So here is my V input voltage. So can I say my V output is same as VBE plus V naught. I'm sorry, Vn equal to. So my V input voltage equal to VBE plus V naught. So now I need to replace VBE with V naught. So here these two resistors, if you look at RE, which is VBE here, and RL, which is V naught here. So can I use the voltage division rule to find VBE in terms of V naught or Vn? So I'm going to say VBE equal to Vn, total voltage, times the same resistance over total resistance, Re plus RL. So based on this, I'm going to substitute this VBE in there. So Vn, I'm going to pull it to the other side because I have Vn common. So Vn times Re over Re plus RL equal to V naught. So I'm going to pull out the V naught here, or Vn here. So Vn times 1 minus Re is 25 over Re plus RL. We found Re equal to 25. So 25 plus 2000. We end up that value as right here, V naught over Vn equal to 1 minus 25 by 2025, AV equal to 0.987 volt per volt. Okay, now AV naught, which is gain at no load. AV naught is gain at no load. So at no load means, so coming back here, if I do not have this resistor, okay, is there any current passing through this? There is no current passing through this at no load, because since nothing is connected, this load is not connected there, the current passing through this is 0 milliampere. So my VBE equal to 0. So in that case, V naught equal to Vn. In that case, my no load gain is 1 volt per volt. Okay, now we're going to find the input resistance. So input resistance is nothing but looking at the circuit from the input terminals point of view. So here my input terminals are right here, this and the ground. Okay, so here is my input terminals. So I don't need to include the signal, so I can eliminate that. Now let me redraw the circuit. So the circuit is going to be look like this. I have 100 kilo ohm. Okay, this is grounded, and then Re, and then RL, and that's going to be grounded, Re and RL, and from there you're going another direction, which is there is a source saying that GM times VBE and then RC, and this is also grounded. Okay, so this is how the circuit is going to look like. Now I want resistance right here, Rn. Sorry, I need to restart up again to find the input resistance. So here, to find the input resistance, I want to find the resistance between these two terminals. Okay, V input is right here. So to find out the input resistance, what I'm going to do, I'm going to move this resistance connected to the emitter terminal to the base side. When I do that, so here is my base terminal, here I have 100k which is grounded. Now I'm moving that RE and RL, both of them are in series. I'm moving them to the base side. When I move it, this value becomes RE plus RL times beta plus 1. Okay, so basically if you move a resistance from emitter side to the base side, so if you move resistance from emitter to base, multiply with beta plus 1. If you move the resistance from base to emitter, so if I move this 100k to the emitter side, then divided by beta plus 1. Once I move it, this is grounded right there. Okay, so again you have the other source right there, so it's not going to matter much here, because I mean this is not going to contribute any resistance because it's grounded right there. My input resistance is now only this part, so my R input equal to 100k parallel with RE is 25 ohms, RL is 2k ohms. So that is 2025 times beta plus 1. Beta is 200 in this case. So 201. That's the input resistance. So I think I found the input resistance somewhere down here. So here is the input resistance. Now input resistance end up with 80.19 kilo ohms. 80.19 kilo ohm. Now output resistance. Now to find out the output resistance, you have to include the R signal too. To find out the output resistance, we need to include the R signal too. So finding the output resistance between the output terminals. So one of the students asked me, why are we not considering RL while finding the output resistance? While finding output resistance, we do not consider RL because we're assuming, or we're trying to find the resistance between the open terminals. It's just like finding orthothevenin. Okay, what do you do while finding orthothevenin across some element? So when you're finding orthothevenin across output resistance, remove that resistance and then look at the circuit from those open terminals. So we're going to look at the circuit from here. So that's the reason I'm not considering RL. And while finding orthothevenin, you remember, replace all the voltage sources with their internal resistance, current sources with open circuit with internal resistance. So voltage sources usually short circuit, current sources are open circuit. So based on that, I found R out. So to do that, I need to include the R signal. R signal is like 100 ohms. R signal and RBB, they are in parallel. So 100 parallel with 100k is going to be a very small number, 100 ohms. Little less than 100, 99.9897, something like that, but take that as 100 ohms. Now moving that 100 ohms to the emitter side. So when I move it to the emitter side, I'm going to divide that with beta plus 1. So R signal and RBB are in parallel. Then divided by beta plus 1, we end up with 25.5 ohm. That's the output resistance. Now, as usual, GV overall gain is AV times Rn over Rn plus Rsig. This is valid for any configuration CB, CC, CE. And then that value is 0.987 volt per volt. Thank you. I'll stop this video here. Next video, we'll solve more examples of CC configuration. Thank you.